And today I have the pleasure of introducing to you two physicists that carry out their research there. Deborah Harris has 3 degrees in physics from Berkeley and the University of Chicago. She has worked at Fermilab for the last 14 years in the field of neutrino research. Dr. Harris has written many articles for scientific journals, an essay for a book by others who are also scientists, and was chosen to write a blog as part of the International Year of Physics in 2005. She is a frequent presenter at workshops and conferences in particle physics from California to Japan to Spain and to India. Today she'll be presenting a one-person play that she wrote for the inaugural Fermilab Physics Slam this last fall. And while Dr. Harris works in the physics of the very, very small, Chris Stoughton studies the physics of the very, very large. Dr. Stoughton earned his PhD in particle physics from Columbia University in New York in 1987. While at Fermilab, he has worked primarily in the field of astrophysics. His current field of study deals with, among other things, researching the possibility that time might come in discrete particles, just as matter does in the form of protons and electrons. Dr. Stoughton is a frequent speaker at a variety of venues, including Saturday Morning Physics for high school students down at Fermilab.
Well, thank you very much for having me. I've never had an opening band. I really appreciate that. That was a first. So how many of you out there know what neutrinos are? Heard of them before? Breakfast cereal? Japanese rock band? No. Okay, so most people do not know what neutrinos are or why they're important. But they're some of the most abundant particles in the universe. In fact, there are more neutrinos than there are protons or neutrons by a factor of 700 million. Without neutrinos, the sun wouldn't shine, we wouldn't have any elements more complicated than hydrogen, and they were created at the time of the birth of the universe, and they've been around ever since. They've been in every corner of the universe ever since. On the other hand, they are also the hardest particles to detect, because they almost never interact. They don't make up the atoms around us, and often their role is to destroy structure rather than to create it. They are everywhere, but they are never part of our ordinary existence. And the fact that they don't interact often actually makes them very good messengers from places we can't access any other way. You want to see into the core of the sun? You use neutrinos. You want to understand supernova? Use neutrinos. You want to look all the way back in time to when the universe was 1 second old? Study the neutrinos that were there at the time, because they're still here now. But because of this simple fact that they're almost impossible to see, they have a very long and, I think, a very amusing history. I'm here to tell you that history, but I want to do this from the point of view from people that you don't usually hear about telling you about neutrinos. And especially people you don't usually hear telling you about science. So the neutrino first made its appearance in history in a famous letter written by a very famous physicist named Wolfgang Pauli. But if you read the letter carefully, which I'm going to do, you realize that he actually made somebody else deliver that letter. So the first monologue is from the point of view of the reader of one of the most famous letters in the history of science. Zurich, 4th of December, 1930. Dear radioactive ladies and gentlemen, can you believe this? Energy is missing from the atom. We don't understand it, so naturally my superior, Wolfgang Pauli, writes a letter with some outlandish idea to explain it, and he sends me to read it at this conference. As the bearer of these lines, to whom I graciously ask you to listen, will explain to you in more detail, I have hit upon a desperate remedy to save the law of conservation of energy. Mr. Chadwick, over in England, you see, examining radioactive decays where so-called beta particles are made, observed that there was less energy at the end than was there at the beginning. So, Professor Pauli's guess is that there must be some other particle carrying away that energy. But it leaves no trace in the detector, so he reasons that it has to be electrically neutral and not interact too often. But really, if the professor actually believed in this desperate remedy, do you think he would have just sent one of his minions to report on it at the conference? Surely he just doesn't want to face up to Niels Bohr. Dr. Bohr claims that this can all be explained by Heisenberg's uncertainty principle. He says that in quantum mechanical processes, energy is not always conserved. Professor Pauli's excuse for not being here himself does not inspire compliments. Unfortunately, I cannot appear in Tübingen personally since I am indispensable in Zurich because of a ball on the night of the 6th and 7th of December. I've seen the professor dance. He is hardly indispensable. But you mark my words. If this is all bunk, the humble messenger will bear the brunt. On the other hand, if the new particle turns out actually to exist, then Professor Pauli will become even more famous than he already is, and 100 years from now, no one will even remember the messenger's name. have a long ways to go. Anyway, after Pauli, through his student, made this bold prediction, his colleagues were skeptical. Luckily, Enrico Fermi was not so skeptical, and he worked out a theory that described the laws that would govern these neutrinos, based on what was measured in experiments. But as it turns out, Fermi had just as hard a trouble getting his theory published as Pauli did, trying to convince people that the idea for this new particle was sound. So the next monologue is given by the editor of Nature magazine, none other than Sir Richard Gregory. "1934, London, England. Dear Dr. Fermi, thank you for the submission of your manuscript, Tentative Theory of Beta Rays. We regret to inform you that we cannot publish this in our journal because it contains speculations too remote from reality to be of interest to the reader. Sincerely, Sir Richard Gregory, editor of Nature magazine." No use mincing words here. I understand Enrico Fermi is a brilliant man, but this time he has gone too far. This theory he proposes that all these radioactive decays people have been studying take place because a neutron can change into a proton, emit an electron particle, and then this thing he calls a neutrino, simply of no use. I will grant you that the theory in the manuscript does describe the pattern of energies of electrons that come out of these radioactive decays. But Dr. Fermi has had plenty of time to see these results. I would hardly call that a prediction. And I will grant you this too. I am intrigued by the symmetry he proposes. Just as a neutron is like a proton but with its charge removed, the neutrino would be like the electron but with its charge removed. Then Dr. Fermi calculates what would happen when the radioactive decay goes backwards in time. In that case, when a neutrino strikes a neutron, then it would produce a proton and an electron. And here is where any intelligent reader would find something else to do. According to Dr. Fermi's calculations, the neutrino is over 1,000,000 times less likely to react than a proton. How on earth are we going to get millions of neutrinos to test this idea? I tell you, Dr. Fermi has some cheek. He wants Nature, the world's premier scientific journal, no less, to publish a theory about a particle that, on the off chance it does exist, cannot even be measured. I say let him publish his musings in some other journal. He must have a cousin who can arrange for that in Italy. So sure enough, Fermi's theory on beta radiation was published in Italian and German first before it was ever published in Nature magazine. So the next monologue in this series is the one monologue that is based on pure rumor and not on facts or interviews. Some of the principals have even denied that there is any truth to this story, but the rumor is too good to leave in the story. So the character in this case is the divorce lawyer for Leon Letterman's first wife, Florence Gordon. Leon has done many wonderful things in his long and fruitful career, both in and out of the laboratory, and I hope I don't get in too much trouble for telling this story, but anyway, if he ever does find this out. As they say in this business, if you've seen one divorce, you've seen one divorce. I've represented women who were divorcing their physicist husbands many times, but I don't think I've ever learned as much physics for a case as I've learned for this one. Before I started representing Florence Gordon in her case against Dr. Letterman, I didn't even know what the word neutrino meant. But now I can tell you quite a few things about them, and one of the things I learned is that it takes a long time, usually decades, to make progress on neutrinos. Then, as if that weren't bad enough, it takes even longer for the rest of the world to catch up and notice that progress. Just take the discovery of these neutrino particles. They were predicted to exist way back in 1930, but a neutrino wasn't actually seen in a detector until 26 years later at a nuclear reactor. Apparently, the physicist who first proposed that neutrinos existed, Pauli, promised a case of champagne to the first person to see neutrinos directly. At least Pauli was still alive when the neutrinos were discovered. He died 2 years later. I hear that the two scientists who saw these neutrinos first sent a telegram to Pauli to tell them his prediction was right, and to collect their champagne. Who knows if those guys will ever win a Nobel Prize for this, but it certainly seems prize-worthy to me. So what does all this have to do with my client? Well, my client's husband developed a completely new way to study neutrinos. Instead of just putting some experiment next to a reactor to study them, my client's husband used a particle accelerator to make a beam of these particles. The point of doing that was to see if these neutrinos are the same kind as the ones that come from reactors. How on earth did they do this? They took a beam of protons, slammed that into some solid target to make a bunch of other particles, and those particles decay into neutrinos. If you put enough shielding in the way, all the other decay products get absorbed. The only thing left is the neutrinos. See, when reactors make neutrinos, they are making electrons at the same time. But when an accelerator makes neutrinos, it makes muons over the same time. A muon, see, is just like an electron, only a lot heavier. So because one neutrino gets made with a muon, and the other neutrino gets made with an electron, they think that maybe it's just a different kind of neutrino, just like a muon is a very heavy kind of electron. My client's husband proved that this is true because the neutrinos he saw with the accelerator made muons when they interacted in the detector, whereas the neutrinos that you make in a reactor can make electrons when they interact in the detector. And this is where I have to make sure that my client's interests are served. Here she's been married to him for over 20 years, raised their 3 children, and in that time, Dr. Letterman went from a starving graduate student to a full professor at Columbia. Not only that, but he proved that there is this whole new family of particles that are heavier than the ones we know and love. There are probably heavier versions of protons and neutrons too. Someone just has to be clever enough to discover them. But she has had the bad timing to get divorced many years before the rest of the world, including the Nobel Prize Committee, catches up to realize how important this discovery is. I'm going to make sure that the marital settlement includes the fact that the condition that if Dr. Letterman ever wins the Nobel Prize for any of the work he has done during his marriage to Florence Gordon, she gets her fair half of the winnings. So the next character in this monologue is a miner who has spent his adult life digging gold out of the Homestake Mine, which has been in operation for almost 150 years. Leeds, South Dakota, 1985. I've taken the elevator down to the mine with Mr. Davis for over 20 years, and I have to say, I really feel sorry for the man. I know it's tough being a miner. I should know, I've been one for 20 years, but I would have never guessed that it's just as tough being a chemist. If you asked me before I met Mr. Davis, I would have said those guys are all too busy doing stuff you and I will never understand. But you know, when you work in a mine, everybody has to take the same elevator down the shaft. So when they started doing this experiment deep underground, I started riding the elevator with these folks. These guys are a chatty group, I tell you. Anyway, after enough years of rides, I think I figured out a thing or two. I was telling you how hard it is to be a chemist. Can you imagine a job where you build a swimming pool-sized tank deep underground, fill it with bleach, and wait for these weird particles from the sun, which he calls neutrinos, to interact? When one of these neutrinos interacts, it's supposed to change a single chlorine atom into an argon atom. And the only way Mr. Davis knows this is to wait long enough and drain all this, the whole pool to find the handful of argon atoms in the swimming pool. I would call him a magician, not a chemist. So anyway, this poor Davis fellow designs this amazingly challenging experiment. He sees a bunch of argon atoms and proves once and for all that yes, the sun does shine thanks to nuclear energy. Since, he tells me, if it didn't, there would be no neutrinos to change chlorine into argon in the first place. Before now, every time people tried to figure out what made the sun shine, they ended up with a prediction that it should only have lasted a few thousand or maybe a few 100,000 years. But apparently it's been around much longer than that, and even Darwin had that figured out. It's just that nobody knew how. Mr. Davis's neutrinos solved the problem. You'd think the world would celebrate, right? Break out the champagne. But no champagne for Mr. Davis. Instead of calling this a great success because Mr. Davis proved once and for all that the sun does send trillions of neutrinos to the Earth every second, everyone is pointing fingers because the number of neutrinos he measured in the swimming pool was 3 times too small. At least so his buddy, Mr. Bacall, tells me. I've seen how careful Mr. Davis is. He can't be wrong, let alone by a factor of 3. It's Mr. Bacall who must have gotten it wrong. I've tried to cheer Mr. Davis up. I told him, hey, Mr. Davis, those neutrinos probably didn't get to the detector because it's been so darn cloudy these days. He keeps laughing at that one for some reason. Apparently, neutrinos pass easily through clouds, or Earth for that matter, which is why the detector is so deep underground. The ground keeps other particles from turning chlorine into argon. Maybe Mr. Davis should just go do something easy instead, like politics. So, as it turns out, both Bacall and Davis were right. The sun does produce exactly as many neutrinos as Bacall predicted, and Davis measured exactly the right number of electron-type neutrinos. The reason they can both be right is because some of these neutrinos that were produced in the sun actually changed to another kind before they got to Davis's detector, and that other kind could not be seen by Davis's detector. So, I wanted to tell you how this could happen. It's not that one neutrino was decaying into another. It's that they were oscillating. They were changing, and they would, one neutrino, if you start as one kind, it can become another, and then you change back again to the original kind. And it's the fact that these oscillations happen at all tell us that the neutrinos must weigh something. They must have some tiny mass. And even though that mass may be tiny, even a millionth of the size of the mass of an electron. Most neutrinos are working on, in one way or another, with studying these oscillations. So the next, if we had time, I would give this brief overview, but we'll wait and see people come in. This is the extended version. Okay, so the next monologue is from the point of view of an underground construction worker who was working at Fermilab in the late 90s. March 2001. This has to be the strangest job I've ever had in my 20 years working construction. These guys from Fermilab want us to dig a mile-long tunnel with half of it pointing downhill at a 6% gradient and none of it pointing back uphill. They want this tunnel to make a beam of particles I never even heard of before, neutrinos, and send them to some old iron mine 500 miles away in Minnesota. This job has been one nightmare after another. This long straight part, that's where the neutrinos are made. We're digging that out with a tunnel boring machine, just like we're making another subway tunnel. But once we hit that bad rock, instead of digging out 80, 90 feet a day, we were stuck with all this rock falling down around us, and we were moving forward only 3 feet a day. It's been like that for months. It will never end, I tell you, but everyone keeps chugging down the Red Bull and hoping for the best. They tell me that when we're all done digging this big tunnel, they're going to make a beam of these neutrinos that is 100 times more powerful than any other that's been made. They brought all 200 of us on the job to this big auditorium one day. Kind of looked like this one, actually. But then this physicist gets up there to talk to us. He tells us that they're not just sending these neutrinos through the Earth to Minnesota, they're going to try and catch a few of them on their way out, and then see if they see the same number on the way out as they predicted from the ones they measured on this side of the Earth. This is going to tell us about how much these neutrinos weigh. You would not believe the history of these particles. First, nobody even believed they existed. Then nobody thought they could be seen directly. Then nobody thought they could weigh anything other than exactly zero, even with 30 years of evidence from the sun shining down on them. Now, because these physicists finally believe that neutrinos weigh something and can change from one kind to another as they fly, we're digging this tunnel. And the experiment that goes in it is supposed to make the world's most precise measurement of exactly how much they do change by measuring these particles after they've flown 500 miles. I don't know what medication these people are on, but it is powerful stuff. And here's the part I really won't believe until I see it. We're only digging this tunnel for the first half mile of that trip. For the other 499 miles, the neutrinos will be going through solid Earth. Here it takes us a full day to go 3 feet, and we're professionals. How can something just zip through the Earth without even breaking a sweat? Anyway, so this last monologue is from the point of view of a woman who has spent her whole life in South Dakota and whose daughter is going to college to become a physicist. The same home state line that was home to the first experiment to see neutrinos from the sun is also the home of the Sanford National Underground Laboratory. October 2012. When my daughter and I first received this invitation to see an underground laboratory, I was against it. Why should we take a tour in the same gold mine that has killed so many men in my family? I know, I keep hearing it. Mining has gotten a lot safer now than it used to be, but I've always had mixed feelings about that place. My family has been working in the mine for over 100 years. In fact, my grandpa was one of the miners who excavated that cavern for the first experiment. I figured that when my daughter won that Davis-Bacall scholarship to go to college, we were done trying to earn our living underground. Why go back now? Of course, my daughter was dying to go on this tour, and you know I can't win an argument with her. So we both went on the tour to see what has been done to the mine after the miners left and the scientists took over. Because of this scholarship, my daughter may even work there this summer, believe it or not. It's crazy. I never thought I would see my own child working in a physics lab, but she's practically there. What's next, the White House? After going on this tour, I see that these physicists are not all like those guys on the Big Bang Theory. Okay, clearly some of them are. They especially like to talk during this 2-minute elevator ride down to where the experiments take place. So, just like those guys on Big Bang Theory think that their work is so sacred, these physicists view this mine as a sacred place too. Not just because of what they're doing, but because of its long history. In fact, it's sacred to them also because being deep underground makes their experiments possible in the first place. In fact, while we were protesting the working conditions down in the mine, the physicists were protesting when they were threatening to close the mine. I'm not sure I buy any of this, but these physicists say that they will do experiments in this mine to tell them if their theory of how the universe came to be is correct. They say that in the very beginning of the universe, there were equal amounts of both matter and what they call antimatter, something that can collide with matter and create pure energy. Yet today, all they see is matter. They can make this antimatter stuff in their laboratories, but they never find enough difference between the way matter and antimatter behave to figure out what happened to all the antimatter that must have been around at the beginning of the universe. They say that these neutrinos may provide the answer if they can see that neutrinos behave differently than antineutrinos. And how will they discover this? You are not going to believe this. They were going to make a beam of these particles 800 miles away, all the way over in Illinois, and then send them here to South Dakota. They want to measure how these neutrinos change over time, and then measure how the antineutrinos change over time. And this could tell them if their picture of how the universe came to be is correct. I don't know. Given the crazy stories I heard about neutrinos, I would say you can't predict anything about what they will do next. What I do know is thanks to generations of miners who lived and died here, we might find out that neutrinos are the reason we're all still here, and my daughter's getting a college education. I don't know what she'll discover with it, but I am sure her kids will know a lot more than we know today.